As we heard in the earlier presentation, all minerals have a specific set of optical properties under polarized and cross-polarized light. Characteristics like birefringence, extinction angle, and interference figure are all direct results of the crystal structure and can aid in the identification of a mineral. However, the optical properties are extremely sensitive to small shifts in the crystal structure, leading to various optical anomalies. So in 2018, John White sent samples of muscovite sheets containing flattened crystals of garnet and an unknown green mineral to our group at Miami University for identification and analysis. All of the samples were from the Spruce Pines district of North Carolina, where reports of flattened inclusions like this aren't necessarily rare. Using energy dispersal spectral analysis and single crystal X-ray diffraction, the garnets were found to be almandine, and the unknown was identified as gannite, a zinc spinel. Both of these minerals are of the isometric class, meaning that their properties should be isotropic, or the same in every direction, particularly the index of refraction. So, isometric crystals such as these should not display any birefringence under cross-polarized light, nor should you be able to observe an interference figure. However, this is not what we observed when initially looking at the gannite. When placed under the cross-polarized light of a petrographic microscope, the gannite was not only birefringent, but it displayed a particularly strong biaxial interference figure, which we usually only see in crystals belonging to the orthorhombic, monoclinic, and triclinic classes. These were the findings that we sent back to White, who reported on them in a June 2018 issue of Rocks and Minerals magazine. This is the birefringence that we first observed in the gannite. The crystal here is being rotated under cross-polarized light, and what you would expect to see in an isometric crystal is nothing. The whole grain would be extinct no matter which way the stage of the microscope was turned. However, here you see these different zones of the crystal going extinct at different times, which is known as undulatory extinction. Here is the original interference figure that we observed and reported for the gannite. While you again would expect to see nothing if trying to get an interference figure, here you see a very clear, distinctly biaxial character. However, further research indicated that this interference figure was actually belonging to the residual layer of muscovite mica that we found on the underside of the gannite crystal, meaning that the results noted in Rocks and Minerals magazine are incorrect. So the gannite in this case acted pretty closely to glass. As you can see in the diagram here, the light had to first hit and go through a very thin layer of mica that was on the bottom of the crystal before it could continue through the gannite, which then only weakly disturbed the path of the light, which is why we were able to get such a clear figure for the muscovite. So we experimented with a couple different thicknesses of mica, and it showed that no matter how thin that coating is, the optical properties of the muscovite are always going to dominate. So in order to actually observe the properties of the gannite, we had to totally clear it away. Removing the residual mica allowed for the optical characteristics of the gannite to be observed, and in doing so, this is the interference figure that we saw. While it's certainly much darker and nowhere near as clear as the first one, it is still distinctly biaxial. You can see the isogyres moving around. However, it's important to note here that analysis with a scanning electron microscope is the only way to rule out the possibility of very small inclusions or little flecks of mica within the larger crystal as being responsible for this figure. This isn't exactly possible given the current circumstances, but after having removed all of the mica that we know of, this is the figure that we're seeing. Here is an additional sample from Spruce Pines of a flattened garnet and gannite in muscovite. The gannite is here on the right. You can see a rather large quartz inclusion that's just barely exposed at the surface, and you can see these cuts around the crystal. This window that we cut through the muscovite is what allowed us to actually observe its optical properties. On the left is a garnet crystal that's about 7 millimeters across. So here on the left is one of the first gannites that we observed. It's about 3 millimeters across, and the black inclusions are still unknown. The optically anomalous properties of these flattened crystals aren't unique to gannite, as we also observed it in multiple garnets that we looked at. This book of muscovite from spruce pines, it's about 8 centimeters across, has multiple flattened garnets that you can see within its layers. So using samples like these, we plucked out a couple of those garnets to look at under a petrographic microscope. So this is one of those garnets. It's about 1 millimeter across, and you can see here these edges where it grew up against the muscovite sheets. So this is not the first time that optical anomalies in garnets has been noted. In fact, birefringence in the crystals has been observed as early as 1895 by Matthews, who noted that flattened almandines from an unknown locality in western North Carolina, quote, all showed an optical anomaly, that is, they showed double refraction meaning birefringence. However, the work lacked any further detail on the occurrence. So when we placed the garnets that we had under a petrographic microscope, these particular ones being from Avondale, Pennsylvania, this is what we saw. On the left is a crystal about 1 millimeter across in plain polarized light. You can see it has that very nice red color that you would expect from an almandine. And then on the right is the same crystal in cross-polarized light. You can see it has these zones of uneven extinction, much like the gannite did. And when viewed in a movie, the wavy pattern, that undulatory extinction, you can see it move across the grain. So as far as interference figures, the garnet that we looked at didn't have any coherent figures where we were actually able to observe isogyres. However, the optical anomalies that we observed in both the gannites and the garnets, particularly this undulatory extinction, indicates that the anomalies are stress-induced. So while analysis with single crystal X-ray diffraction still placed the crystals in the isometric class, the optical characteristics are much more sensitive to small variations in symmetry and exhibit this through anomalies. So here on the right, you have a typical lattice. All of the atoms are in symmetrically equivalent positions. The bonding is the same throughout, which is ideal bonding, and this would lead to the typical expected optics of a mineral. Whereas on the left, you can see that some of the atoms have been pushed from their original positions, and this has created uneven, unideal bonding, which has in turn put strain in the crystal lattice. So what could cause the stress that leads to this strain? Usually it's from things like plastic deformation, inclusions of other minerals, impurities within the chemistry, fractures, and other defects. These result in dislocations and lattice modifications that can hold strain in the interior of the crystal, which in turn alters the refractive indices in the strain zone. This is ultimately why we see optical anomalies. The flattened gannites and garnets that we studied most likely experienced initial stress from constrained growth within the muscovite sheets. So they were introduced to it during crystallization. The fractures around the mica can serve to indicate some of this stress. This confinement during growth most likely led to defects within the structure that hold strain even after the crystals have been extracted from the muscovite, which is why we are still able to observe their optically anomalous properties. Thank you.